A sample of titanium was ionised by electron impact in a time-of-flight mass spectrometer. So what we're going to have a think about here is, what does that mean? It's by electron impact in a time-of-flight mass spectrometer. We've got the information about the isotopes, and we've been asked to calculate the relative atomic mass. Now we need to remember that relative atomic mass is the sum of the mass times the abundance of each of the isotopes. We can see that we've got 1, 2, 3, 4 isotopes. So the mass times the abundance, and we're going to sum that. So we've got quite a lot to write out. So we keep all of this mass times abundance, keep going till we get to the last bracket. And these are percentages, so we will be dividing by 100. Now, before we start doing this on our calculator, we can notice that 48 is by far the most abundant isotope. So, of all the isotopes, we're expecting our answer to be closest to 48. If we type all that in our calculator, we get 47.825. But the question asks us to give our answer to 1 decimal place, so 47.8. Then it says, write an equation including state symbols, so we mustn't forget about that, to show how an atom of titanium is ionised by electron impact. So what we need to remember is that in electron impact, high energy electrons are fired from an electron gun and they knock off an electron. So it becomes titanium 1+ ions, and we have an electron. Now it says including state symbols, we need to remember that they need to be in the gaseous state. And it says, give the m/z value, so just a number, the ion that would reach the detector first. So we go back up and we look at our ions. We need to remember that in the time-of-flight mass spectrometer, the lightest will travel the fastest. So the lightest ion that we have has an m/z value of 46. So we just write down that value. Okay, so the next part of the question says calculate the mass in kilograms of 1 atom of 49 titanium. Now, 49 is the mass of 1 mole in grams, so the first thing I'm going to do is convert to kilograms by dividing by 1,000 times 10 to the minus 3, and then I'm going to divide by how many are in 1 mole to find the mass of a singular one. And we'll type that on my calculator and write down the answer. So I'm getting 8.14 times 10 to the minus 26. The next part of the question is saying, in a time-of-flight mass spectrometer, the time-of-flight T of an ion is shown by this equation. And then it's saying that we've got the kinetic energy, so in the spectrum, the kinetic energy of the ion in the flight tube is here. Okay, and it's then given us the time of flight of the 49 isotope, and it's asking us to calculate the time of flight of the 47. Now, there's a little trick to this question, because we could use the expression that they've given us to find from that expression the distance that the ions travel in the flight tube. And that distance will be identical for each of the two ions, and the kinetic energy is equal for each of the two ions. Now, if the kinetic energy is equal for each of the two ions, then what we know is that the mass of ion 1 divided by the time ion 1 takes squared will be equal to the mass of ion 2 divided by the time of ion 2 takes squared. So we could just use this version instead, and this would be a lot easier, because also the conversion between mass number and mass in kilograms is not needed here, because it's going to be the same for both. So we could say 49 over 9.816 times 10 to the minus 7 squared equals 47 divided by our new time squared. If we rearrange that, we'd get time 2 squared. So we're timesing up time 2 from the bottom line, and we're bringing the other items on the left hand side here over to the right. So it becomes 47 divided by 49 times by time 1 squared. We type all that in our calculator and then square root it. So if we were to type all that in our calculator, 47 divided by 49 times by 9.816 times 10 to the minus 7 squared, we're getting 9.24 times 10 to the minus 13. And then if we square root that answer, then we're going to get 9.61 times 10 to the minus 7. Now, they did actually give this to a fourth significant figure, so I might do that as well. And if I do, I get a 4 on the end there, 9.614 times 10 to the minus 7. You could have gone about that a different way, but would have required a lot more conversions of the units.